Good evening. Welcome to the fourth episode of Season 3 of DeBakey CV Live Innovation on the Loose, streaming live from Houston Methodist here in the Texas Medical Center. I'm Dr. Stuart Cord, Director of Innovation Engineering for the DeBakey Heart and Vascular Center. Now tonight I'm delighted to have on the show Dr. David Hughes, CEO of Novosound, who's here to talk about his platform ultrasound technology and integration of it into health and medtech applications. Now, before we proceed, I'd like to invite the audience into our discussions, so please submit your questions via web at polev.com using DeBakey as the username, or text DeBakey to 37607 alongside your question. You can also add your question into the live YouTube stream. Now, Dave, welcome to the show. You're coming in live from a place that's dear to my heart, Bonnie, Scotland, in Edinburgh. So how are you this evening, sir?
I am doing very, very well, and very happy to be on the show with you tonight, Stuart, or tonight for me, early evening for yourself.
It's a little bit late there, and a wee bit cold as I see in the weather. Now, I think the audience want to get straight into it, and I know they're going to be interested in your ultrasound integrated everywhere, so please, let's learn a little bit more about your tech.
Okay, I will start sharing my screen, and away we go. Okay, so my name is Dr. Dave Hughes, and I am the founder and CEO of Novosound. And over the next 25-30 minutes or so, I'm going to tell you about our vision of ultrasound integrated everywhere. So I started the company back in April 2018, so just in a couple months' time, we're going to be celebrating our 5th birthday. We were a spin-out from the University of the West of Scotland to basically commercialise research that I'd been doing into advanced thin-film ultrasound sensors and connected systems. I'm very much a recovering academic now that I've left the university system and gone into the real world to build Novosound, which is a strong IP portfolio built upon core material science and ultrasonic engineering, which I'm going to talk about in depth in this presentation. But everything that I talk about is made and manufactured out of our facility inside central Scotland, just outside Glasgow. I'm currently in Edinburgh, but the business itself is in the better part of Scotland, over in the Glasgow side, west coast. But since we started in the 5 years ago, we've actually built up a global customer base, which I'll touch on as we go through the presentation. So I'm the CEO of the business. I lead the technology and commercial strategy of the business. I'm also the inventor of the core technology underneath that underpins everything that we do. And I'm joined by my chairman, Derek Matheson, who actually spent probably 10 years of his life in Houston itself, in the C-suite at Baker Hughes, where he was the Chief Technology and Marketing Officer. The day after he left Baker, he wanted to come home to Scotland, and he joined me as my chairman of the board. So between the two of us, we really drive the strategy of where Novosound is going to go over the future. We're about 40 people as a team. 70% of that is sensor engineers, mechanical engineers, electrical, software, etc. And everything that we do has engineering and physics at the core of our business. So that's the who Novosound and where we've came from is. So the who of Novosound and where we're from. I'm now going to actually explain what we mean by our vision of ultrasound integrated everywhere. And the way that I like to talk about Novosound in these terms is very much in a past, present, and future way of describing it. So I'm going to start now just by talking about the past, ultrasound as the past. So when I started the business, and one of the reasons I've been to Houston, Texas many, many times is that we were very much looking at the corrosion industry. Corrosion's a massive problem. $17 billion a year for production manufacturing alone. It's very costly to inspect every pipework for corrosion, and it's even harder when that becomes inaccessible or high temperature assets that you need to manage. There is a move towards automated inspection though for corrosion, and the fact of the matter is that regardless of what we think about how to tackle the problems, corrosion will still be ongoing. Corrosion is happening whether or not we like it or not, and there's a huge drive to look for improved planning through detecting corrosion early and reliably, but in order to unlock efficiency savings in monitoring. And I know that this talk is much about medical imaging, but I'll show you how we've actually taken what we've learned through working in the oil and gas industry and where we're going with the medical technology. The main tool that you would use to monitor corrosion or inspect corrosion is actually ultrasound, so sound waves in and out of an object and listen to the echoes in order to characterise what's going on beneath the surface. And that kind of brings me to the core ultrasound technology that Novosound has. First of all, we have to consider what the limitations of ultrasound probes, as you may know them, are. There's poor signal transduction or conduction. If you've got a curved surface like a pipe, or let's look ahead to the body parts, then sensors don't fit curved surfaces or flexible surfaces due to they have a rigid ceramic or rigid plastic facing. If things are at high temperature, the signal starts to break down due to the physics of the ceramics used in the ultrasound sensors. And if you want to see very small defects or get a high resolution image, then it becomes really difficult with ultrasound. Ultrasound is always seen as a kind of poor cousin of MRI, CT, spec imaging, and that comes down to the commercial aspect of building high resolution ultrasound probes. Most of these limitations can be traced back to the actual piezo ceramic materials that are used inside the ultrasound probe and their own limitations. So at Novosound, part of my academic research was to just ask the question, if the limitations of conventional ultrasound sensors can be traced back to the ceramic materials used in manufacturing the ultrasound transducers, what if we just got rid of the ceramic sensors? Basically just said, well, that's the problem, let's find a solution. So I was working at the time in the Institute of Thin Film Manufacturing and Sensing and Imaging, and this is an additive process that enables you to coat large amounts of material with very special coatings, and the one that I was investigating was a piezoelectric coating that could generate ultrasound. That led us to develop, patent, and invent a thin film ultrasound sensor material that was flexible so it can bend around a pipe or a body part. It's high resolution, providing MRI levels of resolution from an ultrasound image, improving your image quality. And it continues to operate at high temperatures. So that's more important in the oil and gas and energy sectors where things are high temperature, 300, 400 degrees centigrade, 600 degrees F. Typically, medical imaging, humans don't get much beyond 38, 39 degrees C. If they do, then ultrasound's the least of their problems. But anyway, Novosound's, the core tech underneath Novosound is this thin film ultrasound sensors. A lot of time we say it's a printed ultrasound sensor, and that's just to give an idea that it's additive manufacturing we use to make ultrasound sensors out of a completely new manufacturing process. Through this, we built some initial early industrial products, the Novosound Kelpie. We call that a shape-changing Scottish legend. This is a photo of the Novosound Kelpie in front of a Scottish Kelpie, which is a horse that changes into a sea creature. And we call that just because it changes shape. It uses the flexibility of the sensor in order to change shape. And we also have the Novosound Belinus, named after the god of fire. And this is our high temperature corrosion monitoring sensor. To focus on the Belinus, just to give you an idea of what it can do, it's a simple probe that you strap on hot pipes and monitor for erosion and corrosion while they continue to operate. This gets used in power stations, process plants, refineries, etc., using the high temperature aspect of our sensors. Of more relevance to the medical imaging audience, our Novosound Kelpie is a shape-changing Scottish legend, as I say, because it can bend and flex around a pipe, and it's used for corrosion mapping, so it's a proper imaging ultrasound tool, much like you see in the hospital, but applied to industry. It's very high resolution for an ultrasound probe, 15 megahertz, broadband, allowing superior image quality to previous ones that were on the market. But the real proof is actually seeing it in this video that I'll now play, showing you the Novosound Kelpie tongue. That's the blue kind of strip. That is the actual ultrasound sensor. So when you actually think about what is a thin film ultrasound sensor, what does it look like, then this video should kind of show the kind of flexibility as it gets wrapped around this 1-inch pipe. Apologies that the hands are in the way, but this video should give you a bit of a feel for what the tool actually does in the industrial sector. Here we're imaging various metal parts and showing the shapes that are on the other side. You can see it bending around the pipe here to unveil the defects underneath the pipe. And this was really good for us. This was our flagship product for a number of years. We grew a global customer base, some Texas and North American customers, but then also right across the world. So even though we're based in Scotland, we've been global from the outset. But that brings me on to what we actually do today, because the products that we had in the oil and gas industry, flexible probes, high temperature probes, were great. They started to sell and we grew a business from it. But our big challenge was that when we launched the Kelpie back in 2020, it looked like this. And every customer kind of came back to us with a whole bunch of questions that said, how big could this printed ultrasound sensor be? Or how small could it be? How many sensors could it have on it? Does it work on humans? We've seen it in oil and gas. Could it work on humans? And also, could it go inside humans? And most of these questions have very kind of soft answers. There's always, yes, it could. It could be bigger. It could be smaller. It could have more sensors on it. It could work on humans. But the question is, are you going to pay us to do that? And we started to find customers and clients that would actually pay us to adapt what the Kelpie could be to fit their applications. We started creating customized Kelpies for a range of client problems. And that really gets to the heart of what we mean by ultrasound integrated. We solve clients' ultrasound challenges and integrate our sensors into their solutions. We've worked putting these Kelpies inside aircraft seating to make smart seats for aircrafts. We put them inside the mouth for 3D dental imaging, and I'm about to show you some of the resolutions that we get from our digital scanner inside the mouth. We're working with PavMed over on the east coast of North America on an intravascular high-resolution imaging sensor. Here you can see it pinched down to, going from a Kelpie, which is about 6 centimetres long, right down to an 8 French catheter, and we're going much smaller than that as well. And the second half of the talk is going to talk much more about our wearable platform that came from work that we were doing with a client on the arm. So to give you an idea of what we mean by high resolution imaging from an ultrasound, we've been working with an Israeli company called D-Sound to do dental imaging for very high resolution imaging around a tooth or a prepared tooth surface. And what you can see here are 3D images showing all 3 tissues of the mouth: the enamel, the gum, and the bone. Typically in dentistry, you would use an X-ray, you'd only see the hard tissues, or use optics and you'd only see the surface of the soft tissue. With ultrasound, especially the Novosound sensors, you get a 3D image of all 3 tissues at the resolution that you commonly get with CAD or with CT or MRI. And that's going to kind of revolutionise the dental imaging market in the years to come. It's going to be moving to clinical trials around about the summertime, and we're really excited about what it's going to do for that industry. So that gives you a flavour of what we've done in the past with our core technology in terms of printing ultrasound sensors instead of machining them, and how we start to integrate them into our clients' applications. So people come to us, say, we haven't been able to do this yet with ultrasound, can your technology do it for us? And then we look at a way to integrate our sensors into their products to go forth. I'm now going to talk about the third word of our vision, the everywhere aspect, and this is where we really get into the medical imaging or the wearable side of ultrasound. And again, think about it in terms of past, present, future. Let's think about ultrasound imaging for a moment. In the past, you used to be in the hospital and you get wheeled off to a special room in the hospital to get an ultrasound done on you, and the radiographer, the sonographer would be in the room waiting for you to come into it. You get your ultrasound, and then you'd be wheeled back to your bed and wait for your results to come. Over the last 10 years or so, this has moved towards point of care ultrasound. Companies like Butterfly, Clario, GE have their V-Scan, and this is all about bringing ultrasound to the bedside, or to the place where you have to the place where you get your treatment. There's still a specialist, there's still an ultrasound expert with you. What we really see is that the future is all in wearable ultrasound. Basically get the ultrasound out of the hospital and into the home environment, or allow people to have ultrasound imaging or ultrasound data coming off their body as they go about their day-to-day. It should be completely, truly non-invasive. They shouldn't even know it's there. A bit like in your Apple Watch, where it can measure your blood heart rate or your oxygen saturation without you even noticing. That's the future of where ultrasound should be going. And Scotland, myself and also Stuart, proud to come from Scotland, we invented diagnostic ultrasound back in 1954, back in the Rotten Row Maternity Hospital just inside Glasgow. And I think it's only right that a Scottish company should be the one that really flies the flag for wearable ultrasound in 2023. It's not a new idea to put an ultrasound into a wearable. Novosound's not alone in this outlook, but we really feel that we're the ones to drive it. Every time that a news article appears about a wearable ultrasound patch, my phone starts to kind of light up with people sending me links of these articles about, the wearable patch that comes out of MIT or the wearable patch that comes out of University of San Diego, and there's other companies working in it as well. And it's great. I truly believe, much like The Guardian have said here, that a stick-on ultrasound patch healed is a revolution in medical imaging. I mean, it's great. Let's get medical imaging out of the hospitals. Completely on board with that idea. But there is a bit of sadness, obviously, because these news articles come out, but they're not Novosound. This isn't Novosound technology. It looks very similar to a Novosound Kelpie with a bioadhesive patch on it, but the news articles are about the MITs and San Diego, University of San Diego's of the world. They're not about a small company coming out of the west coast of Scotland. When you read deeper into these articles, it says, the patch is connected to an instrument that turns reflections into images. So they're still, they attach the patch to the skin, but they're still tethered to an instrument. They're working hard on a wireless version, and they're confident that they'll be able to achieve a wireless version in a few years. MIT, University of San Diego, and the rest in a few years to get to the wireless version of this. And at Novosound, we kind of think that's cute. A few years for some of the best and biggest universities in the world. And Novosound, we've been working stealth for the last couple of years before, where we take our Novosound Kelpie, our flexible ultrasound sensor, we strap it to the chest with a bioadhesive couplant layer, so there's no gel. We can produce images of body parts internally. Here is an ultrasound image of Dan's lung, but we've also done the wrist, the bladder, the chest, other parts. And we're already doing it wirelessly. This photo is actually of the first proof of concept of the lung monitor that I'll talk about in a moment. But really, wireless wearable ultrasound is here already. We were over in CES in Las Vegas showing this off at our booth, showing wireless wearable ultrasound. So I don't see why you have to wait 2 years to get it to come out of the university system, out of MIT and University of San Diego, when if you want to get this done and play about with it, Novosound's here waiting for it. And then you think, what does ultrasound actually measure? What would you use this for? Well, ultimately, ultrasound is a method of looking inside the body at internal structures, getting the mechanical properties, the stress and the strains of tissues out. You get real-time movement data. This isn't a one-shot picture. This is a video from inside the body of both fluids and solids. And you can also get that down into physiological parameters such as blood pressure or hydration status. And I'll go into a few of these. For example, with dehydration, if you work in care, primary care, secondary care, when the elderly show up at the hospital, they can come up with lots of different contraindications. They might have headaches, they might have aches, pains, delirium, constipation, etc. Around about 50% of the time, you can give them a glass of water, a hydrating gummy, and these go away, and they don't need to go into hospital any further. Wouldn't it be great if you could actually stop them coming to making the trip to the hospital and monitoring their hydration status remotely to prevent that, let alone, the 2.2 million children that die of dehydration a year, or when there's a heat wave and tens of thousands of people die from dehydration. With our system, we've shown that we can actually correlate the ultrasound signal that comes from the top of the arm using machine learning signal processing to a relative change in hydration status. What this allows us to have is an actual hardware and software stack to deliver remote monitoring solution for dehydration. And you might think to yourself, well, I'm a surgeon or a high-flying professional in the hospital environment. Do you know how many times I've used ultrasound to measure dehydration in the hospital? 0. And that's fine. When you're in the hospital, you're surrounded by experts who can spot the signs of dehydration. What we're looking at here is outside the hospital. We're looking at it when it's in the home environment or the very busy care home environment. And we truly believe that Novosound has a solution here to monitor dehydration remotely for those who can't monitor it for themselves. We've also worked on a wearable bladder monitoring device. So this was in partnership with the University of Central Lancashire down in England, where we used their expertise in machine learning to build basically a device that could monitor when the bladder is about to empty before it emptied, so you can set off an alarm. And this was to basically save laundry bills for hospital and care home environments. So the idea would be that the garment would be put in, or the sensor would be put in a garment to monitor the volume of bladder, and before the bladder was about to empty itself, then an alarm could be set off to get the person to the toilet in time. Most bladder monitors currently monitor after the fact. They look for wetness in the bedding. Here we could do it before. There's on one half of this side, on the left hand side is ultrasound imaging pictures of bladders. On the left hand side is the Novosound measurement, and that's quite a thing that I'd like to say is a differentiator of the Novosound way of looking at the world, is there value in having a 48-hour stream of an ultrasound video coming out of the bladder, or do we just want the measurement in order to do something useful with it? So a lot of the Novosound technology is designed much more for measurement rather than imaging. It simplifies the electronics vastly, but also allows you to get to information quicker. So here we measure the bladder. From these green traces, we can get the volume using signal processing, machine learning, and geometry to get the volume of the bladder as it fills up. And we found that it was a very accurate against the volume of liquid coming out of the bladder as the gold standard measurement, allowing you to alert the caregivers prior to the event. During the COVID pandemic, we also turned our gaze from the bladder up towards the lung, and this was all about monitoring the pleura, or the wall of the lung, with ultrasound in the home environment, not in the hospital. Again, if you're in the hospital environment, you're surrounded by specialists. This is for the people who are remote or outside the specialist environment. It was driven, like a lot of early stage tech companies, by the COVID-19 crisis, trying to work out how we could help with it. But the key driver here was, how do we keep patients out of the highly infectious hospital environment and out of ICU for as long as possible? So a lot of the time, COVID, if we cast our minds back to the early days of the COVID-19 pandemic, back in the February, March, April 2020, when we didn't really know what was going on. Was it inflammation? Was it respiratory? Was it viral? We knew it affected the lungs. So a lot of the work that we're doing here is driven by, how can we actually monitor the lungs before it gets to a point where you're hospitalised? And if you can monitor the lungs, not only just for COVID, you can actually get longer term data applicable to any lung disease with a simple ultrasound platform. Currently, the gold standard for monitoring the lungs, especially in ICU or in the hospital environment, is X-ray imaging, but that's ionizing radiation. It's a one-shot image, and there's a lot of infrastructure around X-ray. So moving towards ultrasound has a lot of benefits for the hospital environment from this point of view. A typical lung ultrasound will look like this. The yellow arrows are pointing at the rib cage, and the space in between the two yellow arrows are actually the lung, or the wall of the lung. And one thing to make clear here is that because the lung is filled with air, it effectively becomes an acoustic mirror, so you don't tend to see anything below the wall of the lung because all the sound bounces off the lung when it's in a healthy state. When it's a nice big air-filled sac, it becomes an acoustic mirror. As soon as you start to get disease, then the signal starts to change. And that's what we really wanted to tap into. There are papers out there, academic papers in Lancet and other reputable sources that show how, when it comes to sensitivity and specificity, point of care ultrasound actually improves diagnosis of critically ill patients with lung complaints compared to chest x-ray. So we really saw that as a driver of, well, if you can go from medical imaging into POCUS towards wearable, there must be something in it about monitoring people with long-term lung disease, not just COVID, but also like COPD, asthma, etc. So the way that you kind of analyse an ultrasound picture for the lung would be that you draw what's known as A lines, and this is just a recurring reflection from this acoustic mirror behaviour that the lung gives. And what you find is that when the lung becomes diseased or inflamed, or wet, as the description is, these A lines start to disappear as the acoustic wave gets attenuated or absorbed by the wall of the lung. So if you, like we did with the Novosound system, on a healthy lung you get nice spikes coming out, these recurring reflections from the wall of the lung because it's a nice acoustic mirror. But when the lung starts to become inflamed or wet, these disappear. So you've got a good kind of go, no-go signal plus all the steps in between to enable you to build a lung monitoring system with a wearable ultrasound patch. And we presented this at Medica back in 2020 and got a really good response that helped us develop the platform further and we're always on the lookout for new ways of applying this system. So, to recap and pull the presentation to a close, Novosound is very much looking at the future of ultrasound, moving it away from its past in the hospital, even bedside, towards its wearable future. Who knows, maybe in 5 years or so there'll be an ultrasound around the band of your smartwatch. That would be my ultimate goal. It would allow us to see a shift from clinical ultrasound, where you have an ultrasound machine, you have images, you measure it by drawing little diagrams and little arrows on black and white pictures to get to diagnosis. So basically all this clinical experience, time and cost, don't get me wrong, we're never going to completely get away from that. There's a reason hospitals exist and we're glad that they are there. But there is a future of diagnostics where we've seen it in a lot of other aspects of healthcare. Ultrasound should be part of that vision, allowing automated remote information diagnosis for things such as blood pressure, quite widely seen as the holy grail of wearables would be to have an absolute or even a relative that's accurate measure of blood pressure going up or down, dehydration. We do a lot of work in bionics about looking at tissue movement, but there's so much more stuff that ultrasound is used for in the hospitals that I want to bring into the house. So, when we talk about Novosound being ultrasound integrated everywhere, that's what I'm talking about. And thank you for having me on the show to explain that. And I'm happy to kind of delve deeper through Q&A, or I'll end there.
Well, thanks for that, Dr. Hughes. That was a really interesting presentation. I love how you're bringing a little bit of Scottish mythology into your working environment, and you talk about the better part of Scotland being on the west coast, so a little shout out to all those people out there that are protecting the west coast, especially the Pollock Fire Department who are on the night shift at the moment. Okay, so real quickly, I want to just touch on the tech a little bit more. Okay, this was obviously created was at the university that you were at the time, and you got the IP wrapped up. But what really, in a nutshell, is this underlying tech that you have? What makes it so different from all the other tech that's out there?
So the main IP, intellectual property patents that Novosound has is in the manufacturing of the ultrasound sensors. So a lot of the time ultrasound sensors tend to get made out of ceramics or piezo composite materials, which are rigid, quite bulky materials, and they have to be machined into certain sizes or shaped. And that's quite a complicated behaviour. I used to spent 15 years as an ultrasound PhD student right through postdoctoral studies and onwards, making ultrasound probes using the traditional methods. And this was all with a view of making them very high resolution and better image quality. But the failure rate was so high and the yield of ultrasound sensors was so low that I started using thin films to basically deposit ultrasound sensors, print them rather than machine them. And that increased the yield, making them commercially viable at scale, which lends itself to the wearable application. But then also, because you're starting with nothing and building up the dimensions of the ultrasound transducer, you basically already start with a high resolution probe, so you're enabling a much more cost-effective way of making higher resolution ultrasound imaging. And then the third part is that because the manufacturing is all about thin deposition, they're inherently flexible. So you've got an inherently flexible, high resolution and cost-effective way of making ultrasound transducers that basically lends itself to the mass market adoption. We started in oil and gas because that's where we could see an opportunity, but really where this technology really lends itself is the everywhere aspect of our vision. But as a company, our IP is very much in the material science of how you actually make ultrasound sensors. That's the core heart of everything that we do. The next level above that is how we actually engage with clients to get it out there and build the sensor stack on top of that.
I mean, I think, you hit the nail on the head there. It seems like you've got a very attractive way of creating this to scale. All right, and am I right in thinking that you use kind of techniques that are out there in the semiconductor industry, like chemical and physical vapor deposition, that type of thing, or?
Yeah, exactly. Everything that we do in our manufacturing, I set up the company, left the university, we had an empty room, we had to build a thin film centre, so we've bought a plasma vapour deposition unit that does the atom by atom or molecule by molecule deposition for the ultrasound sensors. We then had to do flexible printing of circuit boards, which we actually acquired a company to do that, so that we could do that in-house at the speed that we wanted to go at. But a lot of what we're doing here is taking, as you say, semiconductor techniques and applying them to the manufacturing of ultrasound sensors, allowing you to really unlock a lot of applications that haven't been thought of before because the limitations of the previous technologies just wouldn't allow for it.
Got it. And I'm going to hit on some of the applications. You showed a slide earlier of using this for teeth and dental applications. And just a side note, funnily enough, I was at the dentist there a couple of weeks ago, went to a new dentist, and they got out this probe, kind of put it in the mouth, and they built up a full model, like rendering of my teeth, and it was all optical based, right? So it's like a kind of image based modeling system. So that allows the dentist to actually see the teeth, and then they brought in the near infrared item to look at any kind of cracks or whatever. So how does the ultrasound technology fit into that? What are you able to see?
So the ultrasound scanner that we're building is very much complementary to the optical scanners, and the optical scanners are phenomenal technology. The work that 3M and 3Shape in particular have done, phenomenal image quality, and the speed in which it can create the 3D images of the inside of the mouth is amazing. The limitation there though is that it's surface imaging. It's an optical camera that builds up a 3D surface with, taking the photography aspect of camera to give it the right colour, etc. But it's very cosmetic, it just looks at the surface. With the ultrasound tool that we're building, you get to see inside the tooth, so not just using fluorescence or near infrared to look at cracks or subsurface, because a lot of the PhD that I actually did was, the title of my thesis was Optical and Ultrasound Detection of Tooth Decay. So we really looked into infrared spectroscopy for imaging the teeth, and the depth that you get there is maybe 0.5 millimetre, 500 micrometers maximum, whereas with ultrasound you're getting millimeters in up to a centimetre. You don't tend to go too much of a centimetre into a tooth because the tooth tends to only be about a centimetre big. But in terms of getting the high resolution 3D subsurface imaging in a live image is where ultrasound really comes in on its own. So you could imagine a device in which the optical scanner creates a very high resolution 3D surface of the inside of the mouth, and then use the ultrasound tool to colour in what's going on underneath the surface. Where is the periodontal pocket? Is it swollen? What's inside the periodontal pocket without using a metal prodder to probe it? What's the erosion status with the enamel dentin junction? Are we losing more enamel than we want to? And then you even get into 3D characterization of caries lesions. Are these active caries lesions? They're lesions. They're going to cause rampant tooth decay. You're really just unlocking so much more information that typically you would get with a one-shot 3D X-ray picture with all the ionizing radiation, but getting that from an ultrasound picture in a live feed. Effectively the dentist would no longer be blind as they drilled and filled, because they could actually track what was going on inside the gum as they do the surgical treatments. But wow. It's very much a complementary tool to the optical scanners, because they are very good at what they do.
And is that system available for purchase now, or like?
I would love it to be. I've been working on dental ultrasound for about 10, 15 years since my PhD. We've got a client that we work with out in Israel called D-Sound, and that's moving to clinical trials over the summer. Got it,
and that's really interesting. Now, I saw that really nice slide of your bladder image there. Can you maybe pull that up? Because I'm noticing on the left-hand side of the screen, you're seeing the more traditional ultrasound image that maybe more of the audience are familiar with. But then on the right-hand side, you've got the data stream that you guys are picking up. So I'd like to kind of know a little bit more about, how do we interpret that data stream on the right-hand side?
Okay, so this kind of, you're absolutely right, it's different in that on one half you get what the highly trained sonographer or the radiographer would see with their years of training to look at ultrasound pictures in black and white, and then you get our one-dimensional amplitude graphs. What we're trying to build at Novosound is the removal of visibility of these kind of graphs. Our end users, so not our clients, the people who buy our clients' hardware that has our software inside or has our devices inside, should never see these measurements. All they should see is either an alarm going off saying, get that patient out of bed, they're about to wet the bed, or they should, basically just get a user interface that just gives them information rather than data. What we've got on the screen here, both the ultrasound pictures and the green traces, is very much data. And it means something. The green means something to me, the black and white means something to an ultrasound expert. What we're trying to build at Novosound is move it towards that information diagnosis, where these simplified traces, so both of these kind of pictures, the black and white, full images of the bladder, and the green traces show the same thing, but one's just been distilled down to a simplified representation, i.e. the top the top graph shows one kind of main feature that you can kind of see just above the white arrow, and that's the front of the bladder wall, and there's nothing really after it, as the bladder's in some state. And then the graph that's on the bottom, where you get the two features, one's underneath the green horizontal line and the purple horizontal line, is showing the front of the bladder and the back of the bladder. From that you can then measure the volume of the bladder. The partners that we have, University of Central Lancashire, have the IP and the algorithms to actually take this data to extrapolate towards a bladder volume, but ultimately whoever's got this system would never see, the actual end user or the person who's wearing the garment with the ultrasound sensors would never see this data, because at the end of the day it's data, it's not information. They only want to see the information, or they only want to be treated by the information and the actions that come out of the information.
Got it. So it's very much like application driven. It's like you said, you're not giving them this patch to use as an imaging modality like they're always familiar with. This is like, no, this is a new way of picking up ultrasound that's kind of tailor-made for your application, and you have your own algorithm processing, that type of thing. So so essentially here it looks like the bladder is full at the bottom and the bladder is kind of empty or not full in the top, right?
The top. Yeah, okay. Exactly. And a lot of the drive that you see from the research institutes that come out with patches of ultrasound, a lot of the time they look at, this is going to enable you to have a 48-hour stream, video of the heart beating for 48 hours, but at the end of the day, who's going to watch 48 hours of beating hearts? Whereas if you can distill that down to simplified imagery. So as low exposure as possible in terms of sound waves or whatever, but then train algorithms and train with signal processing algorithms, machine learning, etc., to tease out when there's something wrong that you then have to get a clinician to look at the state of the heart. That's where we're kind of looking at is getting it simplified enough that we can automate as much as possible. One of the goals is to stop, to reduce the number of people who go to hospital, to reduce the amount of time that people spend in hospital by getting it to be much more automated. That is needed at the kind of at the appropriate times. We're not saying you never need an ultrasound image again. What we're saying is that for the specific use cases that we're trying to apply this to, there's simplified approaches that don't require full video streams coming out of the body.
Yeah. And if I was looking at this real time, is there any latency involved there? Like, is it a nice transient response? You're seeing stuff like an oscilloscope screen almost.
Yeah, exactly. I mean, a lot of the time when you simplify it down to less sensors, so you're not doing full beam forming or 128 different focal planes, and then doing a composite image, you get much faster data because you're right down at you're getting closer to the speed of sound without all the algorithmic image processing that goes on to create the image. And then because you remove the operator's speed of analysis as well, we are looking at really speeding up the kind of time it takes to not only collect the measurement but also create the diagnosis and do that while the person's going about their day, so they don't have to stay still. Basically one of the biggest challenges with ultrasound is the kind of motion artifacts you get if the patient's moving or if they're uncomfortable, or if the thing that you're trying to image inside the body is also moving. You get huge motion artifacts problems. By stripping it right down to measurement instead of imaging, you should overcome a lot of those challenges.
Got it. So again, just so I got it clear, if going back to the bladder example, if that bladder hypothetically could become full within a second, for example, you would see that signal almost real time moving. It's not like it's taking 10 minutes for you to see it. It's right there, right then. Okay, got it.
Yeah, it's one of the things that I much prefer about the biomedical area versus the oil and gas areas. Corrosion takes a long time to build up. You're talking micrometers of corrosion a day. Here, if the bladder is filling up over the course of seconds, then you will see it.
Got it, understood. And again, using bladder as an example, what is the penetration depth of your ultrasound tech?
So with the bladder, that was really when we were looking at how deep you can go, because we are operating at higher frequencies, which have attenuation challenges as you get higher. We use a lot of match filtering and signal processing to recover depth, and with the bladder, I think we're getting about 20 centimeters or so depth into the bladder. This was very much the use case here was in toddlers and young children, so the actual depths were restricted. But a lot of the time we look at it on a case-by-case basis, and for the resolutions that we can provide, we are getting exceptionally deep down because of the recovery that we can do on the signals.
Oh wow, superb. And again, I'm going back to my acoustic knowledge. Will the sound wave go through air like a lot more than it will through water? Will it be attenuated more? So if you put in a balloon,
frequency wouldn't go through air at all.
Okay, right.
That's why you tend to get the ultrasound gel all the time. So with air at these frequencies, it just wouldn't propagate, because we are in the above 15 megahertz, so we go anywhere between 15 megahertz up to 50 megahertz. Dental applications, we tend to use about 50 megahertz, which gives you about 0.01 millimeter of resolution inside the soft tissues, but you maybe only get 5 millimeters of depth penetration. When you get down to the 15 megahertz, you start to get the long depths into the body, which allows you to. It's always a trade-off, and we're trying to kind of really push the limits of that trade-off to get the good resolution and the depth at the same time. So
you get a lot of backscattering if you had applications where there's air pockets and that type of stuff, like the lungs, for example, right?
Yeah, exactly, and that was one of the reasons with the lung monitor that we were only looking at the wall of the lung. We weren't going into the alveoli or the actual, deep into the lung. We were looking at the actual wall of the lung instead.
Got it. So shifting gears really slightly in the interest of time, just going into your kind of progression at the US market, for example. So you mentioned the collaboration and the partnership we have with PavMed. So you want to just touch on that, like when can we expect to see maybe a product on the market?
So I'm really optimistic about this partnership. We signed it back in the fall time. I'd call it the autumn, but it's the fall time. And the progress that we've been making on this has just been phenomenal. The imagery that I'm seeing inside the labs from our, taking our Kelpie, which is about 6 centimetres, the smallest we'd ever done was probably about half that. We're now like right down at an 8 French catheter and going, beyond that. And, I would say that, it's within like the ballpark figures. What we're saying is about 24 months to find a market or to find a product out into the market. But really, in this relationship that we have with PavMed, we are the sensor technology company providing our technology into product that PavMed will take on. So ultimately, they will decide decide how it goes out into the market and when and the timing, etc. Very early days at the moment, but the stuff that we're seeing at the moment is really phenomenal.
And I guess, how do potential customers link up and work with you? If I wanted to do something, I mean, we've talked about this obviously, but if someone here at TMC wanted to test out your tech, how would they go about that, and what can they do?
So the best thing is just to reach out, and we operate a very simplified kind of 3-phase model with our clients, especially new technology such as this, where the first phase is just saying, does our technology work? So we always try and answer this question of does Novosound thin film ultrasound sensors do X for the client? And that's very quick. We do that as either as a development kit or an evaluation kit, or even just a small package of work that we do at our facility in Glasgow. If that's successful, we then move into a development contract to actually apply the technology to a proof of concept device for the client. That might be a technology readiness level of about 3 to 4 or so. And then when that's all well and good, then you get into the productization, and that's when you actually start looking at how does this product get licensed, how does it get launched, how does it get put into the market. At the very early stages, if there's anybody at your institute at Hughes Methodist who wanted to try this out, then as I say, the best way is to reach out and just give us an idea. We can sign NDAs and hear about your ideas or how you feel ultrasound could be applied in a wearable platform or the imaging platform where they've not been able to do it in the past. And it always just starts with a conversation and see whether or not it piques our interest. Does it solve a problem for the person on the other end of the phone? And then just go from there. Though we pride ourselves on being really easy to work with and really rapid. We're not talking 3 years to design a brand new ultrasound probe. We've turned things around in 2 to 3 weeks rather than years. And that's kind of one of the strengths of the IP that we have, is that we can do very customised ultrasound sensors very quickly.
Great. Well, I think on that note, I think it's a nice note to wrap up on. It's been great having you on your show, Dave. Really looking forward to maybe have you on again a year or so. When those products are hitting the market and we're doing stuff. And again, you're in Scotland, so please watch out for those haggises, kelpies, and unicorns. Okay, so again, Dave, thank you very much. I'd like to thank the audience as well for tuning in, and this will be on demand on YouTube very soon, so watch at your discretion. Thank you, everyone. Goodbye.
Thank you very much.